She has been she has been an IEEE Fellow since 2011, an honor that reflects her outstanding achievements and leadership in the field. Her accolades include the IEEE Aerospace and Electronic Systems Society Barry Carlton Awards in both 2011 and 2012, the 2019 Eurosep Journal on Advances in Signal Processing Best Paper Award, and the 2019 H. Mimno Award. She was also recognized with the 2008 Fred Nathanson Young Engineer of the Year Award and the IEEE AESS Board of Governors Exceptional Service Award for her exemplary editorial leadership. Professor Grieco has played pivotal roles in numerous international conferences, serving as journal chair, technical program chair, and organizing committee member. She has also been the lead guest editor for many special issues focused on radar signal processing. She is currently the president of the IEEE Aerospace and Electronic Systems Society 2024 to 25 and holds a long list of past prestigious roles, including editor in chief of the Eurosip Journal on Advances in Signal Processing. She is also the former vice president for publications and IEEE AESS and distinguished lecturer for both the SPS and AESS. Her research spans a wide spectrum from clutter modeling to CFR techniques, waveform diversity, cognitive radars, and the integration of sensing and communications. She has authored over 250 scholarly works, contributed to several book chapters, and has worked closely with both academia and industry. Her mentorship has shaped a generation of top tier researchers and engineers now contributing across prestigious European institutions and organizations. It is truly a privilege to have her with us today. Please join me in giving a warm welcome to Professor Maria Sabrina Greco. Thank you.
Thank you everyone for the very nice introduction. And I'm quite happy to be here and in this workshop and to talk to you about radar systems and advanced radar signal processing with application of AI. I think I can start now.
Yeah. Within 2 seconds, we can start. Just
Yes.
I formally open the workshop. So
Yes.
the workshop is supposed to be inaugurated by our director, Professor Manoj Singh Gaur, but he is unfortunately not available for inauguration. So we may open the workshop. So with a warm welcome, we are inaugurating the workshop. So now the workshop is declared as open, handing over to Professor Sabrina to start with the workshop, the lectures.
Thank you.
So I'm stopping my sharing, so you can share your slides and start.
Okay, now I can share my slides. Thank you. So let me proceed. Where is it? Okay. Can you see it?
Yes, slides are visible.
Good. So just introduction, more details on the topics of this course. So we will start today with passive radars. We will go through the bistatic geometry and the radar equation, then the bistatic radar principles, the source opportunities for passive radars, then the bistatic ambiguity function, the star bands cancellation. Then I will say something on target detection and tracking in passive radars. And I will show you some example of real systems that are implemented in practice. Then after passive radars, we will touch upon the MIMO radars. We will see two different MIMO radars collocated and widely separated radars. We will focus on collocated MIMO radars. We will see MIMO waveforms and also one of the most important aspects of collocated MIMO radar, that is the virtual array and then the beam pattern. And I will show you also some practical example of MIMO radar. Then we will continue with the continuous wave radars, CW. We will see some example of frequency modulation patterns. Then we will focus on linear frequency modulated continuous waveform radars. We will see a typical signal processing algorithm of the continuous wave radars, that is the ramping or the chirping. And then we will see also some of the application of the continuous wave radars. And then we will go through also some MATLAB sessions for implementing some of the easy signal processing algorithm that I'm going to introduce in the next lectures. So now we can go directly to the passive radars lectures. So one recommendation, at the end of the day, each day there is a Q&A session. But if there is something that is not clear during my lecture, you can anyway stop me for asking explanation. Don't be shy, please. And if something is not clear, maybe because the internet connection is not good, please let me know immediately. And if I'm too fast and then you don't understand what I'm saying, again, please stop me. Let me know so I can slow down or I can repeat what I have said. So make this course useful for you and then interactive. So please ask questions if you don't understand and stop me if there is some problem. Okay, now let's start with the concept of bistatic and passive radars. So now we will go ahead for about 1 hour and then we will have 15 minutes of short break. Okay, so these are the topics that we are going to see today and tomorrow on passive radars. Passive radars are bistatic radars, but bistatic radars can be also active bistatic radars. So we will start first with the concept of the bistatic geometry, so the radar equation and the radar cross-section, bistatic radar cross-section. Then we will see the bistatic range and velocity. And after that, we will focus on the characteristics of passive radars. So the different sources of opportunity, the power budget, the DPI cancellation. You will see what the DPI is. Then we will analyze the definition and characteristics of the bistatic ambiguity function, and then the typical passive radar signal processing. Then we will say something on the multistatic passive systems, and we will see some example of real passive system. So let me start introducing the bistatic geometry. Then in a the difference between a bistatic radar and a monostatic radar is that in the monostatic radar, both receiver and transmitter are in the same location. In the bistatic radars, either active or passive, transmitter and receiver are in two different locations, and they are separated by the baseline. In this figure, you see that the baseline is called L, capital L. Generally, this is the notation that we use for the baseline. So the distance between the transmitter and the receiver. Then you see also the extended baseline. So it is on the same line of the baseline, but external to the distance between the transmitter and the receiver. So the line, the interval between the transmitter and the receiver is the baseline. On the same line, but outside the baseline, we are on the extended baseline. Then you see that there is a target and a distance between the transmitter and the target, and we call it R sub t. Then the distance between the receiver and the target, it is R sub r. And then the bistatic angle beta that actually characterizes the system. So the bistatic angle beta is one of the important parameters of the bistatic radar configuration. And you see also here in dotted line the bisector of the bistatic angle beta. Now let's look at the other angles. Alpha between the baseline and the R sub t, and gamma, the angle between the baseline and R sub r. Clearly, in all the triangles, alpha plus beta plus gamma is equal to pi. Then we have theta sub t, that is the angle between the north direction, that here is n, as you can see on the left-hand side of the figure, and the r sub t, so the distance between the transmitter and the target. Then we have also minus theta r, that is the angle between, again, the north direction and the distance between the receiver and the target. Using the rules on the angles of the triangle, then we can say that the angle beta, so the bistatic angle, is equal to theta t minus theta r. Okay, so these are parameters that are quite important in defining the bistatic radar, and then they will appear in all the slides, next slides on passive radars. So many of the properties of the bistatic radar depend on the geometry of the bistatic radar. The radar equation, the Doppler velocity, but also the radar cross-section and the coverage area of the bistatic radars. Then we have already said that the bistatic angle is the angle between the R sub r and R sub t. So going back here, is the angle between the distance transmitter target and then target receiver. Now, Based on this angle, the value of this angle, actually we can have three different regimes. When beta is less than 20 degrees, then we can say that we are in the monostatic geometry. When beta is between 20 and 145 degrees, then we are in the bistatic configuration. That is exactly what we are going to focus on. When beta is between 145 and 180 degrees, then we talk about forward or fence radars. This is a particular kind of radar that we are not going to analyze in these lectures. So here we have a cartoon showing the monostatic and the bistatic geometry. As you can see, in the monostatic geometry, receiver and transmitter are in the same location or quite close. So the beta angle is small. But in the bistatic geometry, we have the baseline that we have seen before and the beta angle. In this figure, the names of the distance between the transmitter and the target and the receiver have a slightly different names. Instead of R sub R and R sub T, we have R1 and R2, but the geometry doesn't change. So everything that I already explained in the initial geometry, it is here in these figures. And this is the forward radar geometry. Actually, this is the extreme where the bistatic angle is exactly equal to 180 degrees. This is a very special configuration with a very special kind of scattering that is called forward scattering. So this needs different signal processing and different models for everything. So we will detail this configuration, the bistatic radar configuration. Now, let's go back to our transmitter and receiver and our target. Again, the distance between the transmitter, the target is R sub T, the target and the receiver is R sub R, and the distance between the transmitter and the receiver is called baseline, and it is R. Now, let's define the contours where the distance between, the sum of R sub T plus R sub R is a constant. Why we look at this bistatic distance? Because actually, when the radar transmit or there is another source of opportunity that transmits some signal, then the signal hit the target and a part of the energy goes from the target to the receiver. So the overall distance that is done by the signal is R sub T plus R sub R. In a monostatic radar, the signal goes back and forth. So the distance actually is twice the distance between the transmitter and the target, because transmitter and receiver are in the same location. Here, transmitter and receiver are in different locations, so the distance run by the signal is R sub T plus R sub R. and we consider the locus of all the points with this constant distance, and it is an ellipse where the two focal points are occupied by the transmitter and the receiver. Okay, so this ellipse that you see here is the locus of the points where the sum between r sub t and r sub r is constant. Okay, the targets line on the transmitter receiver baseline zero bistatic range. Here, the bistatic range is r sub t plus r sub r. And of course, going on this ellipse, the bistatic angle changes, but the bistatic range, so the sum r sub t plus r sub r is constant. Okay? Now, let's derive the bistatic radar equation in a way that is quite similar to the way we derive the monostatic radar equation and also the signal to noise ratio. So let's look at the again at the bistatic geometry. We have the transmitting antenna with a gain that is G sub t, and the peak transmitted power is P sub t. Again, the distance R sub t. And then on the other side, we have the gain of the antenna, receiving antenna, G sub R, the distance R sub R. And then we have the target with a bistatic radar cross-section that we call sigma sub B. Now, on the side of the transmitter, we have the power density that is PT times GT. Of course, it is divided by the surface of the sphere whose radius is r sub t. So we have PT times GT divided by 4 pi RT squared. Then the energy that is, or the power, sorry, that is collected by the bistatic radar cross-section and then sent back to the receiver is PT times GT divided by 4 pi RT squared times the bistatic radar cross-section. Okay? Now the density of the power density that goes towards the receiver is the power transmitted by the target times GR divided by 4 pi R sub R squared. Then this energy is collected by the antenna, the receiving antenna. That's why we should have here the equivalent area of the antenna that can be written as a function of the gain of the antenna itself, but also the wavelength of the radar. So overall, we have PT, the power, the received power is PT GT divided 4 pi RT squared, sigma B divided 4 pi R sub R squared, then GR lambda squared, where lambda is the wavelength of the system, divided by 4 pi. So this is the power received by the receiver, okay? That is backscattered by the bistatic target, by the target. Then, to calculate the signal to noise ratio, then we need to calculate the power of the noise. So the power of the noise is K, that is the constant, T sub 0, that is absolute temperature, then a B, that is the bandwidth of the system, F, that is the noise figure of the system, and then K times T sub 0 BF is the power of the noise. So here there is also another quantity that is L sub P. L sub B indicates the losses of the system. As in the monostatic systems, there are also in each bistatic system some loss that can be due to the signal processing, can be due to mainly to the differences between the nominal behavior of the system and the real behavior, operational behavior of the system. So it can be some losses in the transmitter, some losses in the receiver. Can be also losses due to the age of the system, in the sense that when you put the system on the field, it has some specific characteristics, but over time, the system changes for the use, and then we can have some losses due to the aging of the system itself. So L sub P indicate some losses in the system compared to the initial nominal signal to noise ratio. So the overall signal to noise ratio in a bistatic system, and then the overall radar equation in a bistatic system, depends on some parameter, radar parameter, so PT, GT, GR, then RT, RR, T sub 0, B, F, they depend on the radar. Sigma lambda also. Sigma B, that depends on the target, the bistatic radar cross-section. And then we have also the distances R sub T and R sub R. Now, looking at this radar equation, you should immediately see the difference between the monostatic radar equation and the bistatic radar equation. In the monostatic radar equation, instead of having RT squared, RR squared, then we have a single distance because receiver and transmitter are collocated. So we have the generic R, but it is R to 4 instead of having RT squared, R sub R squared. So here we have two terms that are important in the signal, in the radar equation, the two distances. In the monostatic case, we have a single distance because receiver and transmitter are in the same location. Then we have two different gains for the antenna because we have a transmitting antenna and a receiving antenna, so GT and GR. And we have also a bistatic radar cross-section that does not the same values as the monostatic radar cross-section. So we should pay attention also to that. So here again, in these slides, you can see that here something that I already said. So that is important to have to look at the product between RT and RR, because here we have these two terms. And it is also important to see that the signal to noise ratio is very high for targets that are close to the transmitter or close to the receiver. So let's go back to this. Here we have the term again, RT and RR. So the signal to noise ratio is quite high when one of the distance RT or RR are small. This is a difference with the monostatic radar, because in the monostatic radar the distance is only one, and then you have a high signal to noise ratio when the target is close to the radar. Here, the signal to noise ratio is high when either the target is close to the transmitter or close to the receiver. So there are, say, two different positions in which the signal to noise ratio is high. Then here in the signal to noise ratio, we added two terms, ft squared and fr squared. Actually, in some book, these terms are not highlighted because generally they are included in the definition. They are included in the measure of the radar cross-section, because these are the pattern propagation factors. Ft is the pattern propagation factor between the transmitter and the target. F sub r is between the target and the receiver. So they depend on multiple factors, and it's quite difficult to separate them from the measure of the bistatic radar cross-section. Okay, so they appear in the radar equation. Sometimes they appear, sometimes they are not. But in the measure of the radar cross-section is very difficult in practice to separate them from the radar cross-section itself, because every time you have a propagation through a medium, whatever the medium is, then you have a propagation factor. Okay. Now, let's go back to the bistatic radar equation, and then let's look at the contour where the product between RT and RR, so the two distances, are constant. This contour where the product between RT and RR are constant are called ovals of Cassini, or Cassini ovals. Don't confuse these Cassini ovals with this ellipse, because on this ellipse the bistatic distance, so the sum between RT and RR, is constant. Here on the Cassini ovals, the product between RT and RR is constant. It means that if we keep constant all the other parameters, PT, GT, GR, lambda, the radar cross-section, and the T sub 0, of course, B, F, and the LP, on this contour, the signal to noise ratio is constant, okay? Because the product between RT and RR is constant. Again, let me repeat. On the Cassini ovals, the signal to noise ratio is constant. On the ellipse, the bistatic distance is constant. So these are two different contours, two different points locus, and with different characteristics in the bistatic geometry. Now let's go to the bistatic radar equation, radar cross-section. In the bistatic radar cross-section, the definition is quite similar to the definition of the monostatic radar cross-section, but the bistatic angle has a very important role in the values of the radar cross-section. So you see two examples of the dependence of the bistatic radar cross-section on the bistatic angle and also on the frequency. So see here we have the same target, and but we have frequency that is between 2.25 and 3.75 gigahertz. And in the second figure, we have we have a frequency that is a little bit lower, so 0.15 and 0.25 gigahertz. You see the bistatic angle on the x-axis on both figures, and on the y-axis you see the values of the radar cross-section measured in square meters. So you see that changing the bistatic angle, so changing the configuration of the bistatic radar, the values of the radar cross-section can change some order of magnitude. In the first figure, you see that we pass from 0.1 meter square to 100 meter square. So there are 3 order of magnitudes. And in the second figure, we have more than 2 order of magnitudes of changes, changing the bistatic angle. So we need to take into account also this aspect when we work with the bistatic radar, passive or active. So here we see a kind of target with this shapes, kind of airborne platform. Is very very simple because there are the kind of fuselage in the center and the wings, but quite easy. And then you see the comparison between the monostatic radar cross-section and the bistatic radar cross-section. You see that here we have is a function of the expect angle for 2 different bistatic angles. See here, you see that it changes a lot. Okay, so we need to pay a lot of attention on this radar cross-section, bistatic radar cross-section, and also the angle of the angle, bistatic angle. For some angle, the bistatic radar cross-section for some target can be much greater than the radar cross-section in the monostatic. So you see here on the left-hand side, you see the monostatic radar cross-section. On the right-hand side, you see the bistatic radar cross-section measuring dB per meter square. And you see that for some values, the bistatic ambiguity function can be higher, is higher than the monostatic one. Okay, so they are not the same. So when we consider the bistatic radar, we cannot simply replace the values of the radar cross-section that we measure for a certain target in the monostatic configuration, because the values can be quite different. Now let's go more into details in the bistatic geometry, and you see here again the transmitter, the receiver with the angles that we have defined, theta sub t minus theta sub r. The distances are t, are r, the baseline L. And now we define with the Cartesian coordinate the position of the transmitter, xt, yt, zt, and the receiver, xr, yr, zr, and the position of the target, that is x, y, z. You see again the bistatic angle beta, the bisector, so we have beta sub over 2, and then how can we measure the RT and RR, okay, based on the Cartesian coordinate? Of course, RT is the root square of the sum of the three coordinates, so between the differences between the target and the transmitter. So x minus xt squared plus y minus yt squared plus z minus zt squared. Very similar definition to for the distance between the receiver and the target, but now we have, of course, the coordinates of the receiver. And we already said that the bistatic range is the sum between RT and RR. And this is the distance that the signal transmitted by the transmitter itself run between the transmitter and the target, and then the target and the receiver, okay? And the bistatic radar geometry can be completely specified in terms of any three of the four parameters. So the four parameters are theta t, theta r, L, and r. And remember that r is the sum between RT and RR. Okay? So a little bit of math here, just to see the relations between the different parameters that appear here. So you need to look back at the figures, but they are quite easy actually. So it is possible to write the RT, so the distance between the target and the transmitter, as a function of the distance between the target and the receiver, the baseline, and also the angle theta sub r, so the angle that you see here between the north and r sub r, okay? And this is the equation. So r t squared is r squared plus the baseline squared plus 2r sub r, L, and the sin of theta r. Then if you replace RT with the expression R minus RR, then you simplify and you get both the R sub R as a function of the bistack distance, the baseline, and theta R, and the same for RT. Now, a quantity that is quite important, that is the delay, so the time that the signal, in which the signal goes from the transmitter to the target, and then the target to the receiver. That is r, so the bistatic distance divided by c, that is the light speed, okay? So since r is again the sum between rr and rt, then we can replace this quantity here, and then we get that the delay, okay, can be expressed as a function of the distance between the receiver and the target, the bistatic, the baseline, and the angle of theta. Actually, it is possible to write the same delay as a function of the transmitter parameter, so RT and theta t. Okay, so here the delay is expressed as a function of the receiver parameter, that is R sub R and theta R. But it is possible, since there is a clear relation between RT and RR, is it possible also to express the same delay as a function of the transmit parameter. Here, generally, we use the receiver parameters, okay? So this quantity is quite important because it will appear in the next derivation. Now, let's go back to the ellipse that we have seen in the first slides. And here you see the bistatic range. On the curve, you see the bistatic range measured in kilometers. And on the x-axis, you see the x measured in kilometers. And on the y-axis, you see y measured in kilometers. And all the contours, so you see the transmitter, the receiver, and on the ellipse, you see numbers 5, 10, 15, 20, etc. This is the bistatic range R. So the sum between RT and RR. See, there are all ellipses. Of course, when you go farther and farther from the receiver and the transmitter, these ellipses tend to become circles, okay? But when you are close to the receiver and the transmitter, you have clearly this ellipse, where the transmitter and the receiver are the the focus, okay? Now, as in the monostatic radar, we need to define the range cell. So the bistatic range cell is defined as the separation that is called also delta RC between two cofocal concentric isorange contour. So you see this ellipse, and you see this distance delta. But in the ellipse, the distance between these two ellipses is not the same along all the angles. It changes depending on the bistatic angle. It is a maximum when you are orthogonal to the baseline, see, on the upper part of the figure, you see max delta RC, and it is minimum when you are on the extended baseline, okay? So there is a difference with the monostatic radar, because in the monostatic radar, the radar is at the center. So the distance between two contours is always the same, whatever the angle that you consider. But in the bistatic radar, the distance, so the range cell, has a dimension that is different depending on the bistatic angle itself. So it is minimum when you are on the extended baseline, and it is maximum when you are orthogonal to the baseline. This is important because, I mean, in the definition of the range cell, the dimension of the range cell, the dimension of the range cell is not everywhere the same, okay? So here you see two ellipses where the bistatic range in the two ellipses is different. The difference is 1 kilometer. So say that in the smallest ellipse is 10 kilometers. In the other ellipse, the largest is 11. So R, say that is 10 kilometers in the smallest ellipse, and it is 11 in the largest ellipse, okay? So the bistatic distance is 10 and 11 on the two ellipses. But if you look at the difference, local difference between the two ellipses, on the extended baseline is only 0.5 kilometers, so 500 meters. And orthogonally to the baseline is 1.28 kilometers. So see, the distance, the difference between the two bistatic ranges is 1 kilometer, but depending on the angle, you can have a distance that is less than 1 kilometer or is greater than 1 kilometer, okay? So this is important in the bistatic configuration. So the bistatic resolution, similar definition to the monostatic range resolution, is the ability, is defined as the ability of the radar to separate two or more targets on the basis of range, and then we have the range resolution, velocity, and then we have the Doppler resolution, and then the angle, and we have the angle resolution. So generally, for the range resolution, we say that the range solution is given by C divided by 2B, where B is the bandwidth of the signal, okay? So quite similar to the monostatic definition. It means that the difference between the two ellipses, okay, the two ellipses that you have seen here, okay, here I say that the difference between the two ellipses, so the difference between the two bistatic ranges is just 1 kilometer. And then this 1 kilometer, I mean, if you want to see two different targets, the difference between these two bistatic ranges must be greater than the range resolution. So must be greater than C divided by 2B. But remember that actually, okay, this is the difference between the two ellipses, so the two range, bistatic range. But the delta RC that we have seen here, okay, the real distance is different depending on the bistatic angle. So if you look at the geometry of the system, this range resolution, delta RC, depends, of course, on C, depends on B, the bandwidth of the system, but it depends also on beta, where beta is the angle, okay? The bistatic angle. So the bistatic range cell is also called the physical range resolution. So we generate echo separation of C divided to B. So echo separation is practically the distance, the difference between the two bistatic ranges. Delta RC is the physical distance between the two targets. And this physical distance, we have seen that depends on the bistatical angle, so depends on the position of the targets, if they are orthogonal to the baseline or on the extended baselines. And then the physical distance is this one, C divided 2B, cosine of beta divided by 2, where beta is the bistatic angle. Okay? So just a second, because I need to drink some water. 1 minute.
Sure, sure, sure.
Okay. Sorry for the interruption, but I needed some water. Okay, to drink some water. Now, another very important parameter in the bistatic geometry is, of course, the bistatic velocity. So if you see in these lectures, we are analyzing parameters that are quite similar to those parameters that we look at in the monostatic geometry. And the monostatic geometry, we look at the radar equation. We have seen the radar equation and the bistatic geometry. We look at the radar cross-section, so we have seen the differences between the monostatic and bistatic radar cross-section. Then in the monostatic radar, we look at the distance between the target and the radar, and we look at the range resolution. We have seen the same for the bistatic radar. Now, in the monostatic radar, we generally look at the velocity and then the Doppler frequency, because that's an important parameter that we want to estimate in the target. But here, of course, we have a bistatic velocity. The velocity is defined as the derivative of the distance. So it is practically the change, represent the changes of the distance as a function of the time. But now we have the bistatic range, the bistatic distance, that is r. And r is the sum of RT, so this distance to the transmitter, plus the distance to the receiver. So the bistatic velocity is the derivative of the bistatic range r with respect to the time t. So derivative of RT plus the derivative of r sub r. And then we have two velocities actually. One with respect to the transmitter, so is v sub t x, and the other one is v sub rx. So the sum of the velocity with respect to the transmitter plus the velocity with respect to the receiver. Okay, now how can we derive the two velocities? Well, we write RT and RR using the Cartesian coordinate. So what we have seen here, and the position, we suppose that the receiver and the transmitter are still, so only the target is moving. So X, Y, and Z changes with time. XT, YT, ZT, and XR, YR, and ZR are fixed because the radar platforms, so receiver and transmitter, are still. Then they are constant. So we derive X, Y, and Z with respect to the time, and this is what we get. So it's a complex expression that depends on the coordinates, depends on the velocity with respect to the x, y, and z coordinate. Okay. Now, this is the, expression. Now, let's look at the geometry. Then the Vtx, that is the derivative of the distance rt with respect to the time. If you go here, you see that, look at the target. The target has the velocity v. That is the vector of the velocity of the target. This vector can be decomposed in the two components. One along the distance between the target and the receiver, that is called Vrx, and the other along the distance between the line between the transmitter and the target, and is called Vtx. Okay, you see that we have v, that is the real velocity of the target, and then we have two components, one along the target receiver distance and the other one along the target and transmitter distance. Then we have the angle delta, that is the angle between the velocity vector v and the bistatic bisector, that the dotted line that you see there. So you see delta is between v and the bistatic sector. Okay, so that is delta. And then from the figure, we can derive that actually the velocity, so the component Vtx, so the component along the distance between the target and the transmitter, can be written as v. V is the velocity of the target that you see here. And then is cosine or delta plus b divided by 2. The other component, so along the receiver distance, so drr, can be written as v, same target velocity, cosine of delta minus beta divided by 2. So this is the geometry. We can derive this from the geometry of the system that you see here. As I already said, delta is the angle between the target velocity vector v and the bistatic bisector, okay, measured in a positive clockwise direction from the bisector. Then v, we have said that it is the sum between the velocity along one direction and the velocity along the other direction. So if we do the sum, v cos delta plus b divided by 2 plus v cos of delta minus b divided by 2, developing the expression of the cosine of a sum of difference of angles, then we derive that it is equal to 2v cos delta cos beta divided by 2. Now, we have already written expression that relates the cosine of this beta divided by 2 to the other parameters of the radar. So if you go back here, let me see. Okay, here actually, oh, we have this. So you see that RT squared is equal to R squared plus L squared, etc. And here see that there is a function of cosine P times 2 plus theta R. So we have a relation with the sin of theta R. And we have these relations between RR, RT, and the angle theta R. So using similar relations, we can write that cosine of beta is a function of RT, RR, and the baseline. This is cosine of beta. But we know the cosine of beta divided by 2 is the square root of 1 plus cosine of beta divided by 2. So it means that cosine of beta divided by 2 can be written in this way. So we have 1 over 2 plus, then we have cosine beta divided by 2. But cosine beta can be written as a function of RT, RR, and then this is the expression that we get. So replacing cosine of beta divided by 2 in the expression of the velocity, of the bistatic velocity, then we get that the bistatic velocity is v cosine of theta square root of these quantities. This is the expression as a function of the receiver parameters, r sub r and theta r, but we can derive a very similar expression as a function of the transmitter parameters, so r sub t and theta t. So you see that the bistatic velocity is a complex expression, a function of the velocity of the target v, the angle delta, and the radar parameters. So the distance between target and the receiver, angle theta r, or the transmitter parameters r sub t and theta t. Of course, also the baseline L that is always present there. So let's look at the plot of the bistatic velocity. So here we are in a Cartesian domain, so we have x axis in kilometer and y axis again in kilometers. So you see that curve are the curves with the same bistatic velocity, but the azimuth of the target is 0. So see the azimuth, you see that, and you see also the arrow there is the direction of the velocity of the target. So here in this figure you see v, okay, the burgundy arrow is the velocity, is the velocity vector. Here the velocity vector is the black arrow. See? So if the direction of the velocity is that one, then the white curves are the curves of the constant bistatic velocity measured in meter per second, of course. Okay? Now, let's change the direction of the velocity. Same absolute value, okay? So the velocity, the absolute value of the velocity is the same. But if we change the direction, changing the direction changes this angle delta that you see here, okay? If you rotate the velocity v, then you change delta. And changing delta, you change also the component along the two RT and RR. So you change VTRX and VRX. And you see that the curves, the black curves, are completely different. See here and see the other ones, okay? Now the velocity here is 90 degrees. See, these are the curves. So they changes, okay, with the direction of the velocity of the target. Okay.
Sorry, Professor Sabrina, for interrupting. Actually, we have a 15-minute break in between. So can we declare a break for a few minutes, then we'll start? Actually, 2 to 15, there was a break.
There was a break in the internet connection, or there is a break in the class, in the lecture?
There was a break in the lecture. Actually, we declared 1 to 2. There will be one class, then there will be break.
Okay, so I think that it's time for a break.
Yes, yes, that is the time.
Okay. Okay, so 15 minutes break. Okay,
Yes.
I'll stop here. Okay, I'll be
Okay.
back in 15 minutes. Okay, I think that we can start.
Yes, yes, Professor Sabrina, you can start.
Okay.
And next break will be something around the 3:30.
Yeah, so I will go ahead with for 55 minutes and then we will have a long break.
Yeah,
Is that fine? Okay.
yeah, that's fine. Perfect, perfect.
Okay, so let's then look back at the velocity. So the what we have seen is that if this is the definition of the bistatic velocity, then we need to look at the bistatic Doppler frequency. So practically we divide the velocity by lambda, and we have that is 2v divided by lambda cosine of delta cosine of beta divided by 2. Okay, so it means that the targets on the baseline, they have a zero Doppler. Now we have to define also in the bistatic case not only the bistatic Doppler velocity, but also the bistatic Doppler resolution. Generally, the Doppler resolution relates to the coherent processing interval. So we know that if we, for instance, in a pulsed active radar, if we increase the number of pulses that we integrate, we increase the Doppler resolution by exactly the number of pulses that we integrate. So the Doppler resolution is inversely proportional inversely proportional to the coherent processing interval. So let's see, suppose that we have two targets that they are co-located. So practically they have the same bistatic angle and they have also the same bistatic bisector. Now you see that we have two different velocity, V1 and V2. So we have two angles, delta 1 and delta 2, but beta is the same. So in this case, the Doppler frequency of the second target is 2v2 divided by lambda cosine of delta 2 cosine of beta divided by 2. Very similarly for the other target, for the target number 1. Of course, the difference is in the velocity and in particularly in delta, so the angle of the figure. Now, from this equation, that delta V practically, for a sufficient bistatic Doppler resolution, the difference between the two target velocity vectors projected onto the bistatic vector is this delta V, so is the modulus of V1 cosine delta 1 minus V2 cosine delta 2. Then this, okay, this is equal to lambda divided 2 time integration cosine of beta divided by 2. So the velocity resolution, we see that the velocity resolution changes depending on the angle beta. So for beta that tends to 180 degrees, the velocity resolution degrades. Actually, When the target is on the baseline, so it's crossing the baseline, then we lose completely the velocity and then the Doppler resolution. When beta is equal to 1, then we have exactly the monostatic case. If you go back to the graph and then you put beta equal to 0, it means that the receiver and the transmitter are on the same position, in the same position. So we have the monostatic case, okay? So, this is important because we have seen that the range resolution, going back to these expressions, the range resolution depends on B, the bandwidth of the signal, but depends also on the angle beta, okay? So the bistatic angle. Now let's look at the range resolution, the frequency resolution. The frequency resolution or the velocity resolution, it doesn't matter, it's the same, depends again on the cosine of beta. So now it should be clear that the bistatic angle beta plays a very important role in the performance and the characteristics of the bistatic system, whatever is active or passive. No, that's fundamental. Now, summarizing, we have seen so far the geometry, the bistatic geometry, and you have seen the most important parameters. So the bistatic range, the bistatic velocity, bistatic range resolution, bistatic velocity resolution. And you have seen also the graph and the differences depending on delta and depending on beta. And we have seen also the radar equation in the bistatic case. Now let's move to the passive bistatic systems. So everything that we have seen so far is the geometry. And the geometry can be used in both passive and active bistatic systems. Then everything we have seen so far is true for the passive bistatic systems. Now let's focus on the characteristic of the passive radars. So for the passive bistatic radar, we can use different names. I will use a passive bistatic radar, so PBR, but they are also called passive coherent locators or location, PCL, or they are also called passive covert radar, PCR. And of course, the passive bistatic radars are a subclass of the bistatic radars. As I told you, bistatic radars can be both active and passive. So passive are a subclass of the bistatic radar. Why they are called passive? Because actually they don't transmit any signal. They exploit existing transmitters as illuminators of opportunity. So they use non-cooperative transmitters. So say that in the same area, there are communication transmitters, typically. They can be FM, they can be UMTS, can be 5G, or also digital TV, digital radio. So all these signals that are transmitted for other purposes can be used for locating, for detecting, and tracking the targets. We will see the pros and cons of the passive radars. So fundamentally, passive radar is not equipped with its own transmitters, so it relies on external source of illumination, typically telecommunication transmitters. So in an active system, the radar knows the signal that has been transmitted, okay? And then in the receiver, typically there is a matched filter. Then this received signal pass into the matched filter. At the end, at the output of matched filter, there is the sampling, and we get multiple samples at the output of the matched filter. But the main point is that in an active radar, the radar knows the signal that has been transmitted, so it can have a matched filter. In the passive radars, the radar doesn't know the signal that has been transmitted because it comes from another transmitter, another source. So to build something that is similar to the matched filter, the passive radar needs to acquire also the signal that has been transmitted. That's why in a passive radar there are two channels. One is called reference channel, and the other one echo or surveillance channel. So the reference channel practically acquire the original transmitted signal, okay? In this way, when we have the original transmitted signals, then we can build the kind of matched filter, practically a correlation between the received signal, okay, the signal received from the target, backscattered from the target, and the original signal transmitted by the source of opportunity. And based on this correlation, that normally in an active system is performed by the meshed filter, we can detect the target. Based on the delay, we can estimate the distance, the usual operation of a radar. So the main difference between a passive and active radar is that the passive radar has not a transmitter, but it has two channels in the receiver. And two channel generally corresponds to two different antennas. One antenna is directional and points towards the transmitter, so the source of opportunity. Can be, a direction antenna, or can be in a phase array, so the beamforming is performed digitally, okay? But it is, it points the transmitter, the source opportunity. The other antenna that can be a mechanical rotating antenna, or better, normally the modern passive system have a digitally electronic scanning antenna, so a beam that is formed digitally. And these other antenna, these for surveillance, scan the environment, the scenario, and it is intended for target detection, okay? So we have these two antennas with two different channels, the reference and the surveillance. They are correlated in order to detect the target, okay? Now, let's see the scheme. So you see here the transmitter antenna, and then you see that there are two targets, okay? And these targets backscatter towards the surveillance antenna that is scanning the environment, scanning the area in order to detect the targets. And you see that there is also the other antenna, the reference antenna, that is pointing towards the source of opportunity in order to acquire, to record the signal that has been transmitted. So the primary measurement that is performed by the passive radar, of course, is the bistatic range. Why the bistatic range? Because you measure the delay between the signal that has been transmitted by the antenna, okay, and the time that this signal travel from the transmitter to the target, and then the target to the receiver. So R, that is the sum between RT and R sub R and R sub T that we have seen before. Okay, and we have seen also that the locus of the constant bistatic range, so the ISO range contours, are ellipsoids, where the foci are the transmitter and the receiver position. We have seen this in the bistatic geometry. That's why I explained to you that the geometry is quite important in passive bistatic radars. Then after, together with the bistatic range, we measure also the Doppler shift, the bistatic Doppler shift, or the bistatic velocity. That is the rate at which the bistatic range changes. And we have seen the expression as a function of delta, as a function of beta, okay? Now, actually, we need to locate in a Cartesian coordinate the position of the target. Unfortunately, if we measure only the bistatic range, we cannot locate exactly the position of the target. Why? Because the distance is the same. I mean, in the active radar, this distance is on a circle, and then you estimate the position of the target based also on the angle, the illuminated angle, so the azimuth that the beam is pointing. That is something that can be done also in passive radar. In passive radars, you can use multiple transmitter receiver pairs. So you have multiple ellipsoids. So they have intersection points, and one intersection point correspond to the position of the target. We will see it at the end of this lecture on bistatic passive radars, when we see the multistatic passive radars. But the target position can be estimated using the bistatic range and also the direction of arrival, okay? So the angle that is illuminated by the beam of the receiver. Let me trace some history of the bistatic radar. The first bistatic radar, actually, passive radar, was the first experiment that actually was not implemented on purpose, but it was observed in London. Practically, it was observed by the transmission of the BBC radio. And you see that there is the transmitter in the position indicated by the red arrow, so the VHF FM transmitter that is in Rotterdam. And then you see that there is the Heathrow Airport and bistatic receiver that is in London. Then if you see here that there is the Heathrow Airport, so the aircraft that is the target actually approaching the Heathrow airport cross the baseline between the receiver and the transmitter. So it is possible in some way to see the target approaching the Heathrow airport using the signal that is backscatter, the signal transmitted by the VHF FM transmitter, backscattered by the target. And the first, I mean, this is one of the very easy passive radar created, I mean, implemented in London. But the first observation was not on purpose in the sense that it dates back some decades. Practically was in the science newsletter 38, and this is what it is seen. So there is this very tall television mast in England, is more than 300 meters high. And practically, when the target passes, it creates an echo that goes back to the receiver. And you see that together with the image, so with the that has been transmitted, the receiver receives the echo of the signal that has been transmitted, delayed of some time, and they create a kind of double image or ghost image on the TV screen. Okay, so this is a way in which you can clearly see that it is possible. I mean, you can, at least you can understand that using this scattering, this echo, would be possible to detect the presence of a target. So this double image on the TV screen means that there is a target passing. So the second image is the echo reflected by the aircraft that is passing close to the transmitter. So, I mean, of course, this was not on purpose, but this was a practical experiment, okay? Now, which are the sources of opportunity for passive radar? Every kind of communication signal can be used. Of course, we will see. Since they are not signals designed for radar purposes, of course, they don't have the characteristics that we hope for radar purposes. But let's see the main difference. So FM, the bandwidth is 108 megahertz. The modulation is a frequency modulation. The bandwidth of each channel is narrow because it is 150 kilohertz. The power is highest, 250 kilowatts. So the power density, even at large distance, is decent. What does it mean? It means that actually since the bandwidth, we know that the range resolution depends on the bandwidth. So if the bandwidth is very narrow, then the resolution is bad. If the bandwidth is broad, then the range resolution is quite good. So this is the reason why the range resolution of the FM passive radar is bad, because it is between 1 and 3 kilometers. So for radar purposes, you understand that 1 to 3 kilometers is very bad. But the integration time is quite good, is 1 second. It means that the frequency resolution is 1 Hz. So we have a very good frequency resolution. So what are the cons of this system? That very high coverage, because the EIRP is quite high, but this is the pro. The con is that the range resolution is low, but we have a very high Doppler resolution. Another problem is that the performance, particularly the range resolution, depends on the transmitted information, speech, classic music, rock music. Why? Because it is true that the bandwidth is 150 kilohertz, but the instantaneous bandwidth actually depends on the message, on the transmitted information. So, for instance, for classic music, generally the entire bandwidth is occupied. But for speech, only a small portion of the bandwidth is occupied. So the instantaneous bandwidth is much narrower than 150 kilohertz. And then the range resolution is even worse than the range resolution that we have with the classic music. So the characteristic, we will see the ambiguity function of the FM depends on the content that has been transmitted. Then we have the digital audio broadcasting, so the DAB. The frequency band is much higher. The modulation is the OFDM. It is digital. And the bandwidth, as you can see, is much larger. It is 100.536 megahertz. So it is 1 order of magnitude broader than the FM. The power is a bit lower than we have in the FM, and that's why the coverage is much shorter. But we have a much better range resolution, is 100 meter. The integration time is 0.5 seconds, means that the Doppler resolution is about 2 hours. So the pros, higher range resolution than the FM. The con is that the coverage is lower than FM. Another difference with the FM, and it is a pro of the DAB, is that we have a digital modulation. So it means that the range resolution and then the ambiguity function does not depend on the content that it is transmitted. Whatever is speech, music, or rock music, classic music, the modulation is the same. So the performance of the system does not depend on the transmitted information. Now let's look at the DVB-T. So the digital TV, the frequency band is the order of 100 megahertz. Again, the modulation is digital or FTM. The channel bandwidth is very broad, 6 megahertz, but the power is low, 8 kilowatts. The range of resolution then is quite good, 20 meter, and the integration time is 0.5 seconds. So again, twice resolution. Then the resolution is quite good, the range resolution, also the Doppler resolution. This is a pro. What is the con? Very large. That actually in the DVB-T, the signal is transmitted with a lot of preambles, with the pilots, and so on. These pilots that are useful for synchronization in the communication channel, so they are necessary for the communication performance, creates the side lobes, very strong side lobes actually, in the ambiguity function. And it means that actually the signal, the DVB-T signal, cannot be used as it is for sensing purposes because of these side lobes. So it must be processed before detection in order to cancel or to reduce these secondary lobes in the ambiguity function. We will see it in the next slides tomorrow. We can use also as a source opportunity all the cell phone signals from the UMTS to the 5G, so 3G, 4G, 5G, and in the future also the 6G, when 6G will be in place. The bandwidth is the 3G is 2 gigahertz. We know that for 5G is a little bit higher, but it is still sub 6, so lower than 6G. But in the future, the 6G will be at higher gigahertz frequencies. The modulation of the UMTS is digital, but it is the CDMA, the 5G will be OFDM. And then we have the bandwidth is 5 megahertz. So again, is a very broad bandwidth, but the power is low, is 100 megawatts. Then range resolution is quite good, 30 meters, and the integration time again is 0.5 seconds. So the UMTS has similar properties to the DVB-T and same characteristic in terms of power, in terms of bandwidth, occupied bandwidth. But it has a very low coverage because the transmitted power is low. But again, even though each transmitter has a low power, it is always possible to use a network, to design a network of multiple transmitters. So instead of a bistatic system, a multi-static system. And in this way, fusing the information coming from the different transmitter receiver pairs or simply transmitter receiver, then we can obtain a good coverage also in terms of range. Okay, so we don't discard these sources opportunity because the transmitted power is low, because it is always possible to use everything in a network. Then let's see other transmitters of opportunity, the GSM, so satellite transmission, GPS, GLONASS, Galileo, so we can use these signals also for the passive radars. Or we can use the Wi-Fi. The Wi-Fi signals have a very short range, actually, so short coverage, but can be easily used in indoor applications or in small areas for instance, in parking lots where we can control, or we can track the cars that enter in the parking lot, or also we can track the moving human targets. So Wi-Fi is another source of opportunity. Then there are systems that use multiple sources of opportunity. So on the same mast, there are antennas for different kind of signals, for DVB-T or for FM, for instance. And they use the information coming from all these transmitters backscattered by the targets in order to acquire information on the target position, target velocity, and so on. And they are also able to choose the best signal in order to optimize the performance of the system. So what are the application of passive radars? You understand that even though this is a already mature technology, there are applications in which we need active radars, and application in which we can easily use passive radars. For instance, air traffic control, they can use for detecting low-flying aircraft, also UAV, drones. Keep in mind that since we can use a network, a multi-static network of different passive systems, then we can see the target from multiple perspectives. So even a small target like a drone can be detected by passive systems. Can be used as a surface vehicular traffic monitoring, for instance, on roads, on railways. As I already mentioned, can be used for indoor or local area surveillance, some small areas outside, indoor or outdoor. And can be used also for, a continuous monitoring in dense areas. The main pro of the passive radar is that it does not transmit, so it does not pollute the environment with other EM sources, because it uses the signal transmitted by other sources. But of course, this is a pro, but at the same time, it is a con. So let's see all the pros. Lower cost compared to the active radar, because there is only the receiver, there is no the transmitter. From the military point of view, the defense point of view, the main pro is that since there is no any transmitter, it is impossible to detect the presence of the radar, because in many cases, for instance, the jammers detect the presence of the signal that has been transmitted, and then repeat with some delay, some offset velocity in order to deceive the radar. Or there are the jammers that can direct a strong source of noise to the receiver. So in this way, receiver and transmitter, so in this way, they can blind the radar. But in this way, since you cannot detect the position of the receiver, because it is passive, then the passive radar have a certain level of immunity to the ECM threats. There is no any demand for spectrum resources because there is no transmission, then only reception. And then generally passive radar have a small size compared to the active conventional radar, okay? Because again, there is no transmitter. Then since they are bistatic, then it is possible to detect in some direction a higher radar cross-section. So this, for instance, these stealth targets are designed to be practically undetectable by active radars. So in the direction of the transmission, but they are not designed to be undetectable in, for instance, the forward scattering. And the passive radar, being bistatic, can detect the forward scattering, so the side lobes practically, and then it is possible to detect also the stealth target. And again, another pro is that we reduce the impact on the environment since they do not transmit. So that's why sometimes they are called green radars. So this is the system that we have seen before. So you see the targets there. You see that there are two antennas, one a survey antenna, the other the reference antenna. And there are multiple terms that we need to consider. The blue ones, the solid lines, are what we are interested in because there is the signal that is backscattered from by the targets and they hit the surveillance antenna. So we want to measure, we want to detect the target based on this. Then there is the other antenna, the reference antenna, that records the transmitted signal in order to correlate the original signal with the signal backscattered by the targets. But you see also there are other signals here. First of all, there is the direct signal. The direct signal is the signal that goes directly from the transmitter to the surveillance antenna. And of course, it is very strong because of the distance between the transmitter and the surveillance antenna generally is much, much shorter than the bistatic range. So the signal is much shorter. And you understand that this direct signal must be canceled. Otherwise, it makes the surveillance, the passive radar blind to the targets that has to be detected. And then there is the clutter, of course, that can be due to the bounce on the buildings if you are in urban area, or even from the ground for, the environment, the usual multipart, the usual clutter that we see also in the active radars. So there are terms that are similar to the active radars, so the signals, the useful signals and the clutter, but there is a term that does not appear in the active monostatic radar, that is the direct signal that goes from the transmitter to direct the surveillance. It's not backscattered by the targets. Of course, we rely with passive radars on third-party illuminators because the radar does not transmit, only receive. Okay, so to detect the target, correctly, so to work correctly, the surveillance channel, so the channel that receives the echo coming from the targets, should contain only the target echo and white noise, okay? White noise is unavoidable it is in all the electronic systems. But we should have a high signal-to-noise ratio, so in this way we can detect the target. And also the reference channel should be practically pure in the sense that it should contain only the source of opportunity without any interference. So in this way, we can correlate correctly the surveillance channel, so the echo backscatter from the target, with the signal that has been transmitted. So we build a kind of matched filter. Actually, we calculate the ambiguity function, and then we are able to estimate the range position and also the Doppler frequency of the target in a similar way as the active radar. But in the realistic cases, actually, the surveillance channel contains clutter, multiple echoes, and the signal component due to the reference signal. That is called also direct path interference, DPI. So we will see when we look at the signal processing in passive radars, some way to cancel or to reduce the impact of the DPI. The other problem is that in many cases, the reference channel is not clean, so it contains also interferences. Okay, so ideal case, the surveillance channel contain only the signal coming from the target and some thermal noise with a very high signal-to-noise ratio. The reference signal is clean, so there is only the signal transmitted by the reference, the source of opportunity. Reality is that actually in the surveillance channel we have the signal, the thermal noise, the signal coming from the targets, the clutter, but also the DPI. So the signal coming directly from the transmitter antenna. And in the reference channel, together with the reference signal, we have also multipath and clutter. Okay, so the channel is not clean. Then we will see some of these aspects in the next slides. Now let's go back to the bistatic radar equation. And now let's look at the signal-to-noise ratio. We have seen this signal-to-noise ratio again. Here we introduce the coherent integration gain that is fundamental for increasing the signal-to-noise ratio. It's the same that we have in active radars. Why we are going back to this bistatic radar equation? To have an idea of the signal-to-noise ratio that is available in our passive radar systems. Okay, so again, we have seen this signal-to-noise ratio. I'm not going to explain again the meaning of these terms. I just only want to point out that actually the gain of the antenna GT and GR, of course, depends on the angles of the targets. So the azimuth and the elevation angles of the target, practically the position, the angular position of the target with respect to the transmitter and the receiver. Then there is the wavelength, the usual bistatic target radar cross-section, the noise power, the distances to the receiver and the transmitter, and then G int, that is the coherent integration gain. We have seen already the Cassini ovals. These are the contour for which the product between RT and RR is constant. So the contour on which the signal-to-noise ratio is constant. You see that they have a very strange shape when the distance, when the signal, the distance to the receiver or transmitter are small, but they start to become like circles when we are far from the receiver and the transmitter. It's important to observe that we have a high signal to noise ratio, not only when the target is close to the receiver, that is typical of the monostatic radar, but also when the target is close to the transmitter, because the receiver and the transmitter in a bistatic passive radar plays, in that sense, a similar role, because the signal to noise ratio depends on the product of these two terms, RT and R sub R. Okay, so this is it. We need to remember that the signal to noise ratio is constant on the Cassini ovals, where the product between RT and RR is constant. Now, I already say that in the passive radar, the important product is between RT and RR. In the monostatic radar, to understand the signal to noise ratio, to calculate the signal to noise ratio, the important term is simply R, so the distance between the target and the radar, because of the monostatic configuration. Transmitter and receiver are in the same position. So let's go ahead for 5 minutes more, and then we will have a long break. So let me show you the typical values of the signal to noise ratio in a FM broadcast. And we consider here an isotropic antenna. So it means that the antenna gain of the receiver is 0 dB. The gain of the transmitter antenna also is 0 dB. The transmitted power, PT, is 10 kilowatts. FM is very high power. The carrier frequency is 100 megahertz. The wavelength is 3 meters. So let's look at the signal to noise, typical signal to noise ratio. You see that on the x-axis we have kilometers, and on the y-axis we have again kilometers. So look at the signal to noise ratio when we integrate for a time that is 0.1 second. And you see that the signal to noise ratio when you are quite close to the receiver and the transmitter is high. It can be even 30 dBs. But when you are a little bit far from the receiver and the transmitter, then you see that the signal to noise ratio is 0 dB. This is with an integration time of 0.1 second. In the second plot, we have 1 second of signal to noise ratio, 1 second of integration time. And then generally the signal to noise ratio is increased by 1 order of magnitude. So we pass from 0 dB to 10 dB at the same distance. So that's why when I defined here, I mentioned here the integration time. This integration time is important for the frequency, the resolution, but it is important also for the power budget for the signal to noise ratio. If the signal to noise ratio is too low, then we cannot integrate any, we cannot detect any target. In this case, we consider that the radar cross-section of the target of the bistatic radar cross-section is 10 meters squared. So it's not too small, it's not too big, okay? The system loss 3 dB, the noise figure 3 dB, and so on. So a long integration time is required to obtain an acceptable signal to noise ratio. Now let's see, we have seen the signal to noise ratio, but actually we have the problem is that, as we've seen in this figure, that in the surveillance channel, we receive also the direct signal. So we need to look at the power of the direct signal compared to the power that we receive from the targets, and try to cancel the direct signal, so the DPI, in the surveillance channel. So I think that now we can stop here for a long break. So the break is half an hour. So I will be back here in half an hour. Okay? So
Okay, thank you, ma'am.
take a break. I think we can start.
Yes, ma'am.
Okay, so let me. Okay, so we have seen the signal to noise ratio in a passive radar. And now we see the contribution of the direct path interference or direct path signal, so the DPI. And then this DPI to noise power ratio, so DNR. Then we see here that, of course, the equation is quite similar to what have we seen before, but this time, instead of having the, let's go back to the equation. Here you see we have GT, phi and theta, that are the angles of the target under which the transmitter and the receiver sees the target. Here we have phi r theta r and phi t theta t. These are the angles of that the transmitter see the receiver, and then the receiver see the transmitters. So the gain along that direction for the transmitter and the receiver. Then look at the denominator. In the denominator, actually, we have the distance between the receiver and the transmitter, but that is the baseline. But this time it is only L squared. So the baseline squared y. And here we have RT squared, R sub R squared. Why? Because here we have the double way. So first signal to target and then target to receiver. Here we don't have the back and forth, the round trip. We have only the direction between the transmitter and the receiver. So you understand that even for a large baseline, this DNR can be very high, because instead of having the power of 4 practically as a function of the distance, we have only the power of 2, okay? So the DNR is quite large. Now let's write the signal to direct path signal power ratio. So SGR, that is the ratio between the DPI power that appear here. So you see that you have again the GTGR, but this is for the signal, so this is the signal direction, and GTGR, this is T for this is for the direct path. Then we have all of the baseline squared. Then we have the product between RT and RR squared. And then we have the bistatic radar cross section divided by 4 pi. Okay? Then let's see here, excuse me, an example with the FM broadcast. And we have the transmitter power, that is PT, transmitter antenna. In this case, we do it with the isotopic receiver antenna. On the right hand side, we use a directive antenna. Then again, the usual FM transmission, usual wavelength, baseline, bandwidth, noise figure, and so on. Target radar cross section and target 8. And we look here in the actually is an interference for us. So look at the other figures for isotropic antenna and directive antenna. And you see that actually with large distance, the SDR is minus 125, minus 120 dBs. So even though the signal to noise ratio is reasonable high, so we can have 0 to 5 dBs or 10, 15 dBs, depending on the integration time that we use. Actually, the contribution of the direct pact, so the need to do something to cancel the direct pact interference, the DPI, so to reduce the interferences. Even though we put a directive antenna, it means that we look at the target, okay, with a directive antenna with 88 dB of gains towards the target. See that the shape of the curves is different. It follows the pattern of the antenna that is represented here on the right hand side in the upper part of the slide. You see that the shape of the curve is different, but still, if you look at the values of the signal to direct path ratio, you see that is quite low. So still, even with a directive antenna, we cannot detect clearly the signal in the reference channel. So just a second. I need a second, sorry, because there is some interference.
Okay, ma'am.
Okay, I'm back. As I was saying, the countermeasure measures against the direct path interference are multiple. We can put a shield in direction of the transmitter. Let me go back to the plot here. See, here we have a surveillance antenna when we have the reference antenna. So the reference antenna is pointed towards the transmitter antenna, but the direct signal come direct This is not always possible. So no, it's not always possible to reduce this. And anyway, the direct interference can come also from reflections or bounce from nearby buildings and terrain, and then putting a single shield toward the direction of the transmitter doesn't solve the problem. Or another solution could be to exploit a narrow beam antenna. It means that, again, in the receiver, use the side lobe in order to reduce also the contribution of the direct signal into the surveillance channel. Or we can place a notch in the antenna beam pattern in the direction of the transmitter again. This is possible only if we have arrays. So we can do digital beamforming and we can put a notch in the beam pattern. But typically, the suppression of the interference of the DPI is performed there are two channels. Then we want to correlate the surveillance signal with the reference signal. But of course, we need to do it with, we need to build the ambiguity function. It means that we need to cross-correlate the surveillance signal with the not only the copy of the reference signal, but also with Doppler shifted replicas of the reference signal. So we need to do and also shifted in frequency. And then we do the cross correlation between the surveillance channel and the reference channel shifted in frequency and delayed. Is a kind of implementing a bank of meshed filters. So each filter is matched on a different Doppler frequency. In this way, we practically calculate the ambiguity function, and somewhere we have a peak in Doppler and a peak in range. That means that based on this peak, we can estimate the Doppler frequency and the range position of the target. You can find also this very basic algorithm description of the algorithm in the paper that is cited in the bottom of this slide that has been published. regression time that can be some second long, and you take the reference channel, you shifted it, and you correlate each shifted version times the surveillance channel. So there are many calculations that you have to perform. Now, the effect of the DPI actually, let's see these other the effect. Let me see of the DPI on the clutter multiple contribution. So the problem also of the ambiguity function is that in a radar system, the ambiguity function in the conventional radar system, generally we have one narrow peak in both range and Doppler and low side lobes. This is the active system. But in the passive system, in many cases, we have a lot of side lobes, and that must be cancelled or reduced before using the signal to detect the target. And in some cases also, as you have seen for the FM, the ambiguity functions changes with the time, depending on the signal that has been transmitted. And it means that the structure of the ambiguity function can have, in some cases, unpredictable characteristics. So the ambiguity function, it is quite important in active radar, but here you understand that how the ambiguity function is defined. The ambiguity function mathematically is a function x that depends on two variables, tau, that is the delay, and nu, that is the Doppler frequency. And mathematically is the absolute value of the integral of the complex envelope of the signal, x sub ut, times the conjugate of x delayed by tau and shifted in frequency by nu. So practically, the ambiguity function is the output of the matched filter. The signal, I mean, the filter is matched to the x sub u, so to the complex vector, complex envelope, actually normalized with respect to the energy, as you can see here, so with a unitary energy. But the input of the matched filter actually is a delayed copy of the signal, so delayed by tau, and also shift are the delay tau and the Doppler frequency nu. The ambiguity function has these four important properties. The maximum values is in 0, 0. So when the meshed filter is matched on the right delay and on the right frequency, and the maximum value of the ambiguity function is the energy of the signal that has been transmitted. Since now generally in the definition the ambiguity function we consider the signal with energy equal to 1, so normalized with respect to the energy, the maximum value of the ambiguity function is equal to 1. Second property, quite important, is the constant volume. Means that the volume under the ambiguity function is equal to the square of the energy square. So E squared. If E is equal to 1, then is equal to 1. That's an important property because it means that you can optimize your ambiguity function another problem in some other area of the ambiguity function. Symmetry, quite easy. Simply say that we have a symmetry practically the ambiguity function tau nu is proportional to the ambiguity function, is equal to the ambiguity function calculated in minus tau minus nu. And then the LFM stretching. So it means that if the ambiguity function of a certain waveform is equal to A tau nu, then if you modulate in frequency linearly this waveform, so practically you multiply the complex envelope u of t by the exponential of j pi k t squared, then the new ambiguity function is similar to the ambiguity function of u in the delay, but it is stretched in the frequency along the line nu minus k tau. You will see some example. In a bistatic case, this is a problem because actually what you measure is the bistatic delay tau and the bistatic Doppler frequency. But in the monostatic case, the Doppler, the delay is linearly proportional to the position of the target with respect to the receiver or the transmitter. And the Doppler frequency is linearly proportional to the velocity of the target and again easy to calculate. if you look at the relation between the delay, the bistatic delay of the target and the bistatic ambiguity function, and you look at the expression as a function of the distance between the target and the receiver, or the target and the transmitter, you see that actually the relations are not linear. They depends on square root, and there is the r, there is L, and there is also theta r. This is a complication. It means that if from the ambiguity function you want to calculate the distance of the target with respect, for instance, to the receiver or the transmitter, you the unfortunately, as you can see here, v actually is not the real velocity of the target. V is the projection of the velocity of the target along the bistatic sector. Okay, this v is along the bistatic sector. So it's not easy to calculate this quantity from the bistatic ambiguity function. It means that the ambiguity function, the shape of the ambiguity function, bistatic ambiguity function, depends not only on the waveform that has been transmitted, but also on the geometry of the system. So let's look at it, and we consider a simple Gaussian pulse, and the RL baseline the same. But look at the ambiguity function as a function of the distance with respect to the receiver and the velocity. You see here this ambiguity function as a shape. These are contour. When the angle is 30 degrees. Now the angle t minus theta t is minus 60 degrees. So see here that the ambiguity function has a completely different shape. Then depending on the angle, the bistatic angle, okay, the ambiguity function has a different shape even though the pulse is the same, okay, and the distance from the receiver is the same, but the direction, the moving direction is different, the bistatic angle is different, and then you see a different ambiguity function. Here is a terrible situation. So again, the waveform is exactly the same. The distance from the receiver is the same in all the three plots. The baseline is the same, but the bistatical angle is different. So in some case, you see still can recover the target, I mean, with different resolution. Here, you cannot recover the target and detect the target anymore. So let's look at the bistatic ambiguity function. It's a little bit easier for a chirp signal. A chirp is a typical waveform that actually is used in an active high resolution radar. Here is a toy example. So the duration of each pulse is 0.1 second. The bandwidth is 50 hertz. This is a very narrow bandwidth, but this is a you have a peak around 600 meter per second, so you can see clearly that the velocity of the target is 600 meters per second. Here, again, and also here, you have the same with the zero Doppler cut. The position is 20 kilometers, so you see a peak. So you can detect clearly the target with a range of 20 kilometers and the velocity of 600 meters per second. Same story when we choose theta equal to minus pi. So we have a little bit different ambiguity function, a little bit different cut, but still we have a clear peak in the velocity and in the right range. So we can detect the target. Now, let's look at the bed geometry when theta is equal to minus pi divided by 2. It means that practically the target, so theta r is 90 degrees. It means that the target is crossing the baseline. You see, it is crossing the distance between the receiver and the transmitter. And in this let's look at the ambiguity function for some of the signals that are adopted in the passive radars. So that was the first one on the left-hand side is an example for FM radio, one of the possible transmission. And you see that in this case, the target, the Doppler was 0 and the delay was 0. And you see a peak around 0, 0, but you see also that there are many side lobes here and there. And again, the ambiguity function of the FM radio is time varying. So it depends on the content that is transmitted. The bandwidth, the instantaneous bandwidth depends on the content. So also the range resolution depends on the content. Now let's look at the DVB-T signal. You see here that there is a peak in 0, 0 where the maximum is expected in this case. But there are also multiple peaks here and there that are not that small. There are many. These peaks are due to the shape of the DVB-T signal, where there are multiple pilots that are also periodic. So in the ambiguity function, they build these very strong peaks. They build one on top of the other, and you see here that the power of this peak is non-negligible compared to the power of the useful signal. And if there is a detector here, of course, some of these peaks can be confused for a target. But these are not targets. These are ambiguities created by the ambiguity function, by the structure of the signal. So for the DVB-T, for the television, this is an excellent signal, performs quite well. But for the sensing, this signal is not the optimum one. Now we have also done an analysis on the UMTS signal using some parameter that is typical of the UMTS signal. And we have looked also at the ambiguity function of the UMTS signal. And we looked also at the ambiguity function of the FM, uh, doing some approximation on the FM signal. So you see here, this is the monostatic ambiguity function, and you see a very good resolution in a range and a good resolution on velocity. Now, let's consider the bistatic ambiguity function. Now see that there are all these repetitions here, but still we have a peak here, and we have some resolution in range, we have some resolution in velocity. And here the geometry is still good, but look at here. Here the geometry is bad, and because we are crossing the baseline, and you see that the ambiguity function has lost any kind of resolution in range, is flat, and it has a bad resolution in frequency. So this is an example of what we have seen. We have seen it before for the chip signal, and this is another example for the FM signal. Now, when we have to choose then the best illuminator of opportunity, we need to look at multiple characteristics. In the active radars, we can decide the waveform that we want to transmit based on the ambiguity function, so based on the range resolution that we want, based on the frequency resolution that we want. We can also choose the power, the peak power that we want to transmit in order to set a certain signal to noise ratio, and then probability of detection, and so on. Here, we don't have this degree of freedom because we have only signals that are transmitted by other source of opportunities. The only choice that we have is that in the same scenario, there can be multiple sources of opportunities. Then we can choose which source of opportunity we can use for our purposes. Of course, we can use more than one because, as I have said at the beginning, there are receivers where there are multiple antennas, multiple signals on the same mast. So we look at, first of all, at the coverage, so the transmitted power. We have seen that the power can be quite different. The EIRP can be very different for different sources of opportunities, but also the geometry is important because we have seen that the ambiguity function changes with the geometry of the system. So if the target is crossing the baseline between one receiver and one transmitter, maybe we need to change the source opportunity. So we change the position of the transmitter and then we change the geometry. Then we also need to look at the antenna radiation pattern because that is important for the G, for the gain element in the signal to noise ratio. We need to look at the frequency band because the range resolution, frequency band, I mean, this is because based on that, we need to build different kind of antennas. The temporal coverage, yes, because it is possible that some source opportunity doesn't work all day long, but work only on a short time, and we want to have a 24-hour operation. And then, of course, we need to look at the application that we are considering. But we need to look also at the waveform because the waveform, the bandwidth that determine the range resolution, the sampling frequency, and also the computational burden. And we need to look at the modulation because we have seen that the modulation is digital, then the ambiguity function does not depend on the content. When we look at the analog modulation as the FM, then the shape of the ambiguity function depends on the modulation. Of course, the waveform shapes the ambiguity function, so the side lobes, the side peaks, and so on, and the stability. So the ambiguity function can be time varying in some with some waveform. This is the list of the most used source of opportunities. You've seen the HF broadcast, so AM, FM transmission. Then the DAB that is based on OFDM, the digital TV, also the cell phone, UMTS, and also the 3G, but also the 4G in the future, 5G and 6G, and also the Wi-Fi access. And you see here the modulation of the bandwidth, the ERP, and then you see also the power density. So some of these characteristics are quite important for our application. And the FMA radio is the most frequently used because there are many FM stations overall in all the scenarios. And the power is quite strong, so the coverage is high. The problem, as we have seen, is the bandwidth that is narrow, so the resolution is bad. But the pro is that we have a very large coverage area. And you see here the spectrum of the signal that in the first, I mean, on the left hand side we have the pop music. This is the spectrum. So you see the occupancy of the bandwidth. And on the right hand side you see an example of the speech. And you see that the spectrum is quite different. So since it is quite different, also the ambiguity function of the instantaneous ambiguity function in the first case and the second case are quite different. So that's why they are time varying. Then we have the DVB-T, as I already mentioned, the modulation is the OFDM. The problem is that the original DVB-T used only a single frequency network. So now in the DVB-T, modern DVB-T in some country used multiple frequency networks. So this problem has been fixed, or at least mitigated. And you see here in this graph the bistatic range resolution as a function of the signal bandwidth. The FM is not a point, is a line, because we've seen that actually the FM changes with the content that has been transmitted. And then you see that actually we have a very good range resolution for the Wi-Fi and a bad resolution for the FM. Of course, the power is different, so there are other pros that we need to take in consideration. Now we still have 5 minutes, and then we wrap up, and we have 10 minutes for the question. So let me just introduce the scheme that tomorrow we are going to detail. So this is the scheme that we have seen with the two channels, so the reference channel, the surveillance channel, all the interferences. And tomorrow we are going to see, first of all, how the cross ambiguity function is calculated and some efficient way to perform this calculation. So the cross ambiguity function between the surveillance signal and the reference signal. But we will see also how we cancel the DPI, so the direct signal from the surveillance antenna, surveillance channel, and this needs to be done before calculating the cross ambiguity function. Otherwise, we have a superposition of the disturbance component to the useful signal, and we have seen that actually the disturbance signal is much more powerful than the useful signal. And even before that, depending on the source of opportunity, we could need a signal conditioning, so some processing on the signal that is received from both the reference antenna and the surveillance antenna. This is typical of the DVB-T, for instance. Then we will see, after the calculation of the cross ambiguity function, the cipher detection, so how it is implemented, and then after that, some knowledge on the taking and some example. So I think that at this point, I can say that the lecture is finished for today, because tomorrow I want to start directly with implementation of the cross ambiguity function. Otherwise, it is if I start today, I mean, you will forget. So tomorrow I'd like to start directly with the cross ambiguity function calculation that needs some time. And so for today, I close the lecture, and I wrap up what we have seen today in a very fast way. So if you have some question, please go ahead and ask. I will browse in a very fast way the slides that we have seen today, just to summarize. So first of all, we have seen the geometry of the bistatic system, and in particular the importance of the bistatic angle, baseline, all the other angles. So we consider that this bistatic configuration, when we are between 20 and 145 degrees, this is a schema of geometry. Then we have seen the ellipse where RT plus RR, so the bistatic range is constant. We have seen the signal to noise ratio in a bistatic geometry, and we have seen the Cassini ovals where the signal to noise ratio is constant. The product between the distance to the target, to the transmitter, and the distance to the receiver, the product is constant. We have seen that the radar cross section, the bistatic radar cross section, can change with a different bistatic angle. We have seen the comparison between the bistatic and the monostatic radar cross section. Sometimes the bistatic radar cross section from some angle can be stronger than the monostatic radar cross section. We have seen in detail the geometries. The bistatic range is a function of the distance to the target, distance to the receiver, so the bistatic delay. And we have seen also the ISO range contours. So in the pictures, the range resolution that changes with the bistatic angle. It is minimum when we are on the baseline. It is maximum when we are orthogonal to the baseline. And then so the bistatic resolution depends on beta, the angle. We have seen the bistatic velocity. We have derived the bistatic velocity as a function of the velocity of the target, the angle delta, and the theta t and theta r. So we have seen the plot depending on the direction of the velocity of the target, so the shape is completely different. We have seen also the bistatic Doppler frequency and the resolution that changes again as a function of beta, as a function of the integration time. Then we looked at the system, the passive system, when we have seen the two channels, the surveillance and the reference channels. So some history, I'll skip it. The sources of opportunity, some of the characteristics, some of the applications. And then we have seen the optimum operations of the system, and the realistic case. So we have analyzed the importance of integrating for a long time in order to increase the signal to noise ratio. But we looked also at the DNR, so the contribution of the DPI that is quite strong, so the necessity to cancel the contribution of the DPI. And then some of the countermeasure, physical countermeasure, antenna countermeasure, but we will see in detail the digital signal processing. The importance of the ambiguity function, definition, shape of the bistatic ambiguity function that changes with the bistatic angle. So depending on the position of the target along the baseline, we can lose the resolution. We have seen some shape of the ambiguity function of the signals used in the our passive systems. The list of all the signals that are used, some of the characteristics of the FM, and the blocks in the passive radar. Tomorrow we will see the signal processing chain in details. Okay, so is there any question from the floor?
Hello everyone. If you have any question, please ask to ma'am. Please don't hesitate. Hello ma'am. If anyone don't have any question, then we can close the session.
Yeah, we can close the session of lecture. And if some student has some question, they can also write to me. My email address is in the slide, so they can write direct to me, and I will reply. Okay.
Okay, ma'am.
Yes,
Sure.
yes,
Thank you.
that will be great. If anyone has
Okay.
a question, they can write back.
Okay, so if you have a question, use the email and write to me. Then I'll reply if you have any doubts or curiosity on what you have seen today. Okay, so enjoy the rest of the day or the evening, and see you tomorrow.
Thank you, thank you, thank you.
Thank you, ma'am.
Thank you,
Bye
ma'am.
bye.
Have a nice day.
So, everyone, shall I close the session? Hello, everyone. सब तो चले गए.